All right, so in this video we're going to talk about, or continue talking about, quadric surfaces, and in particular we'll start with the hyperboloid of one sheet. The standard equation is up here in black, and then the example we're going to look at is here in blue. And so we'll approach this the same way we did the last problem. If I take a look in the xy plane, that's of course where z is 0. If z is 0, it leaves me with x squared over 9 plus y squared over 9 equals 1. Which is actually a circle in the xy plane of radius 3. If I go to the xz plane, which is where y would equal 0, I'll get an x squared over 9 minus a z squared over 9 equals 1. Now we're dealing with a hyperbola, and this is going to be in the xz plane. And so x-axis being positive, it's going to look something like this, where that's a 3 and that's a 3. And then finally, the yz plane, where x is equal to 0, and we would have a y squared over 9 minus a z squared over 9 equals 1. And labeling the axes yz, that's going to again give us a similar looking graph, although again the axes are labeled different. So as I start to put this together, one of the things to remember is, in particular right here, as we look down the z-axis, we're going to be seeing this circle, okay? And then if we look down the y-axis, we're seeing hyperbolas, and then down the x-axis, we're also seeing them. And so as I put this together, we've got x, we've got y, we've got z. So looking down the z-axis, you can see there would be that circle. And then those hyperbolas would come into play and make it look something like this. So this would be then our hyperboloid of one sheet. Keeping in mind again, as we take slices of things, as those planes cut through, planes other than the coordinate planes, we're going to have a bunch of planes as they cut through. The traces they're leaving would be of the hyperbolas that you're seeing there. Again, the book's got a really nice picture you can take a look at as well. And I will say, guys, it does get easier. The first time you see this, you might be thinking it's a bit of a stretch to be able to go from that to this. But once you see the combination of what these impressions leave on the planes, it'll be very easy to connect the dots and go from one to the other. All right, so now we're ready to take a look at hyperboloid of two sheets. So the standard equation and then the example we're going to look at. And again, I don't put a lot of stock in memorizing that stuff because if you work it out kind of like I've been down here, it should kind of fall apart around it. So we'll take a look at the xy plane. So the xy plane, this is where we let z equal 0. So y squared minus x squared over 4 equals 1. So labeling x and y, we would have a hyperbola that opens up, and that would be a 1 right there. Let's go to the xz plane, and this is interesting. For the xz plane, this is where y would equal 0. If y equals 0, then in this case we've got a negative x squared over 4 minus z squared over 9 equals 1. Well, that also says x squared over 4 plus z squared over 9 equals a negative 1, if I just multiply by a negative. But a squared quantity plus a squared quantity can't ever equal a negative number. Therefore, there's nothing being left in the xz plane. Okay? And so we would move on then to the yz plane. And if we let x equal 0, we're going to get y squared minus z squared over 9 equaling 1. Labeling the axis, let's say yz. Now we're going to get our hyperbola with a 1 there. All right, so let's see what we have. So I'll go ahead and construct the x, y, z space. And you'll notice you'll be seeing these hyperbolas in the xy plane and the yz plane. And then this xz plane, that's kind of where we have that gap. Now, I've intentionally shorted you on a little bit of information here because I wanted to more so remind you that being a hyperbola of two sheets, this contradiction, this discrepancy is not surprising. That being said, it's also not the full story. Remember, I chose the xz plane where y was 0 and I had this problem. Now, I don't necessarily have to stop at y equals 0. This has just been the case that I've used because it's been easy, it works well. But what if y was 3? If y was 3, think about what would happen there. So let's say y is equal to 3. That's going to be a 9 minus x squared over 4 minus z squared over 9 equals 1. If I manipulate this now, x squared over 4 plus z squared over 9. So what I've done is I've moved these to the other side, so I'll subtract the 1. That's going to equal 8. And that certainly could be something. In fact, if we divide by 8, then this thing ends up being an ellipse. So just because we hit a contradiction here, that is important because that's going to make this thing have two separate parts. But just because we hit the contradiction doesn't mean that beyond it things don't happen. We very specifically selected y equals 0, but if something like y equals 3 came about, that's not to say other things might not exist. Okay, so keeping that in mind, as I said, that's going to be more of an ellipse. So I'm just going to kind of draw an ellipse up here so everybody can see that and see kind of what I'm going to be drawing next. So now that again came along the XZ plane, So what's happening is we're going to have our two parts, if you will, our two sheets, come from along the y-axis, and it's going to look kind of like this, and that's not very pretty, where we've got almost like earmuffs, if you will, coming through there. And I want you to notice again, you've got that space coming from the inconsistency here, but also when you look down the y-axis, which is what this would be doing, what would you be seeing? Well, if I look down the y-axis, that's where I would be seeing these ellipses. Same way, if I take a plane, let's say I take this plane and cut it, that's where these hyperbolas are going to come from as well. So a pretty interesting result from the hyperboloid of two sheets, and one to really pay close attention to. If something kind of weird happens, there might be something a little bit out of the ordinary with this quadric surface, and we would want to account for it. All right, so now for the elliptical cone. So the standard form equation followed by the example we're going to look at. Let's take a look in the xy plane. So if z is 0, if z is 0, much like the last example, the only thing you would get would be a point, so we might need to consider other z values. So if z was 1, then you'd have the ellipse. If z is 2, you'd still have an ellipse, just a different size, etc., etc. So it appears that we're going to have some ellipses in the xy plane. Okay? Then, if we go to the xz plane, this is where y is going to equal 0. So if y equals 0, we have x squared over 4 equals z squared. And notice, if I square root both of those, that's going to leave me with a z equals 1/2 x. But we can't forget about the plus or minus. Okay? And so as I look at the graph of this, if this is the x and this is the z, now we're going to have lines cutting through, all the way through, one with a positive slope, one with a negative slope. Similar in the YZ plane. In this case, x would be 0, so we have a y squared over 9 equals z squared. If I square root, z would equal 1/3 y, but we can't forget about that plus or minus. So that one is going to be very similar, where we call that y, we call that z. We're going to have those lines cutting through. Now again, much like this one, much like the last example, these are just examples of letting a y be 0 and an x be 0. If we let y and x's be other things, we would continue to get lines with different slopes. And so these aren't the only things that are part of our surface. But by putting all this together, and again, as I mentioned, the first time you see this stuff, it seems like a bit of a stretch going from these to this. But once you take a look at what the result is, it's easy to convince yourself that what you're doing is in fact correct, especially with looking at additional pictures. So that's going to again give us the elliptical cone, where those would be our crisscrossing lines you see there. And then as we look down the z-axis, that's going to be where your ellipse comes into play. So something like that. And there's your elliptical cone. All right, so for the final one, we're going to take a look at the hyperbolic paraboloid. And so the equation that we're going to take a look at here is in blue, and we'll handle it much the same way. Now, full disclosure, this one is a little bit harder to see than maybe some of the other ones. But if we're in the xy plane, this means z is going to be equal to 0. And it being equal to 0 would say that y squared over 16 equals x squared over 16. In other words, y equals plus or minus x. And so that's going to give us those lines cutting through like this. Now, we're not quite done yet, because what if we let z equal 1? Well, if we let z equal 1, then we're going to have a 1 equals y squared over 16 minus x squared over 16, which is then hyperbola with a major axis of y. So not only are we testing multiple values here, but we're getting very different shapes. This is the first time this would have happened. We've got a couple lines as we let z equal 0, and then if we go up to 1, we get these hyperbolas. If we continue from there, we will still continue to get hyperbolas, but it's just important to see that we're getting two different shapes at this point. Now, if we continue on to the xz plane, the xz plane is where we let y equal 0, so z would be a negative x squared over 16. And so if that's x and that's y, that's just going to be a parabola that opens down. And then for the yz plane, that's where x is going to be equal to 0. If x is equal to 0, z is going to be y squared over 16, which is then the parabola that opens up, labeling our axes yz. So a variety of different things can happen here, but I will say that when you start seeing things like lines, hyperbolas, parabolas, opening up, opening down, that's usually a trigger for the hyperbolic paraboloid, hyperbolas and parabolas put together. And so when we take a look at this, maybe I'll draw this one up here. This is very, very difficult to draw by hand many times. And so I'll sketch this in, and then I'll try to explain it as best I can through the computer. So what we're essentially going to be having here is a saddle, okay? So we've got this saddle that comes in like this. We've got coming down, coming in like that. And then maybe I'll throw a little bit of a curve in there as well. So I don't know if you can really make that out too well, but this is a saddle where maybe one leg would come over this way, the other leg would go over the other way, the person would be facing this direction. So again, it's my best attempt at a saddle. I would encourage you to take a look at page 740 again. But one of the most interesting parts about this is where all this comes into play. You'll see when you take a look in your text, they have it nicely marked, very nicely marked, where you'll see the parabola and where you'll see the hyperbola as well. And so I would encourage you to take a look at that, and that'll really help you start to see where this comes from. But don't beat yourself up if you're having a hard time drawing that. That's one of those that's very, very tricky for us unartistic people. So there are the quadric surfaces, and again, don't stress out too much on memorizing a bunch of stuff. Just remember to treat them as traces back in R2, and then you can put it all together there at the end.